coming to my last lecture. We're going to wrap it up today by finishing the proof of the main result, which in turn means I'm going to finish the proof of the Band manipulation theorem. Last time I explained the proof modulo 2 ingredients, and both of them I'm going to prove today, and they will be sort of corresponding to two parts of the talk today. The first one is informally says that particle embedding calculus knows more about the boundary of a manifold that you might first think. And the precise statement was the following. We had this manifold with sphere boundary called M partial. It was two connected, smoothable, even stably parallelizable, but we won't be needing the assumption, that assumption for this statement. So it looks roughly like that. We have a compact manifold, there's a sphere boundary, and the boundary is divided into two pieces that are both disks. You can think of it as the upper hemisphere and the lower hemisphere. This is the triad decomposition that I'm going to use. And then I needed a lift as follows. Here we have the space of homeomorphisms fixing the whole boundary. We can forget to only remember a homotopy equivalence relative to the full boundary. Then I can go in embedding calculus land. I forget that I fix the whole boundary, only remember that I fix one of the hemispheres. Go to self-embeddings fixing one of the hemispheres. This means they're isotopy invertible, so like pi 0 of that is a group. Then I go, Then I apply topological embedding calculus to go to that. Then I change the tangential structure from B top D to B odd ED to go to particle embedding calculus. And the map to the cospan category that Sander was talking about gives a map to homotopy automorphisms fixing one of the disks in the boundary of this manifold. And this bottom map is just forgetting that here the homotopy automorphisms are required to fix the whole boundary. So this dotted lift says that, yes. Pardon? Yes, today I'm going to prove a dotted lift as an E1 map, and then you can apply B yourself. Yes. Right. Yes, there is a. I also claim that this dotted map is a loop map, and I do need that. In fact, yes, I do. Okay, so I'm going to prove, and the second part is one of a quite different nature, namely that the stabilization map for orientation preserving homeomorphisms, the double stabilization map followed by the map to odd ED, the orientation preserving variant, followed by the map induced by rationalizing the operand, that composition is null homotopic. Both of these things I'm going to prove today. Let's start with the first part. And I'm going to construct this lift by proving a more general result that applies to more general types of triads than those. So let's pick a triad. Let's call it W to distinguish it from M. This is a compact, d-dimensional topological manifold triad of dimension at least 6. And W is assumed to be smoothable. This will have something to do with convergence of topological embedding calculus needing some smoothness assumption. Then I'm gonna, instead of solving this problem, I'm gonna solve a variation of this problem, which is the following. I consider homeomorphisms of W fixing partial 0, so that part of the boundary decomposition as a triad. And then there is a crucial geometric fact, namely that a homeomorphism of a manifold with boundary automatically preserves the boundary setwise. This is just God given, it sends the boundary to the boundary. So if I then fix some part of the boundary, then the complement of that boundary, which is partial 1, is going to be preserved setwise. So I have by then, forgetting to homotopy automorphisms, I have a map to the space of homotopy automorphisms of W that fix the one part of the boundary pointwise and the other one setwise. Okay. In the derived setting, one way of defining the space is I look at the category of spaces, of two spaces with a map between them. Then I slice over the inclusion of the intersection of the two boundary parts into the moving part of the boundary. And then I take endomorphisms in that category of the inclusion of the moving part of the boundary into the whole manifold and invertible components. This is the sort of official definition, but you should think of it really as homotopy automorphisms of W that fix partial 0 pointwise and partial 1 setwise. Okay, then I can develop a similar diagram. I go to self-embeddings that fix partial 0. I can apply topological embedding calculus to those. And then I can go to particle land. And again, by going to the one-truncated presheaves, in other words, applying the functor to the cospan category, I get a map to homotopy automorphisms of W, where I only remember that I'm the identity on partial 0. But I don't remember anymore that I'm also setwise preserving the other part of the boundary. And then I'm claiming that under some conditions, there is a dotted map like this. And the exercise is to prove, I'm going to prove that statement under some conditions that are in particular satisfied here. And then there is an exercise to deduce the left dotted lift, so meaning the one on the left board, from the right one. And this will be something special to the triad decomposition where the moving part of the boundary is a disk, because it's going to use the Alexander trick. Maybe just to indicate how this works, if I apply that diagram to my triad M circle, then the moving part of the boundary is going to be a disk. So the difference between this space of homeomorphisms and the one fixing the whole disk is the space of homeomorphisms relative to the boundary of the other disk, which is contractible. Okay. So then the result that provides us this dotted lift is the following. This is a version of this result with in a slightly different setting and less general. Was already proved by Michael Weiss, and we give an extension of it in our framework. And I'm realizing I only need the dimension to be at least 5, which I already assumed. So let's say the only condition in addition is that the inclusion of the moving part of the boundary in W is a tangential 2-type equivalence. Then there is such a dotted map. Okay. All right. So I'm going to prove this in a special case that allows me to having to do less bookkeeping. I will discuss the special case, but all the main ideas are contained in this special case. Namely, I'm going to discuss the case where the moving part of the boundary, the fixed part of the boundary is empty. So partial 1 is the whole boundary, so the whole boundary is moving. And then what does the statement say? It says if I take homeomorphisms of a manifold, no condition on the boundary, then I can recover, at least homotopically, the action on the boundary by only remembering the associated equivalence of W considered in this particle embedding calculus land. So particle embedding calculus knows homotopically about the geometric fact that a homeomorphism preserves automatically the boundary pointwise. This is the content of this result. And let's start with something not about embedding calculus, but let's even start thinking about the filler here, which is in particular implied by this one, which is something purely about embedding spaces. Okay, so what is the task in the special case? We have homeomorphisms. Those preserve automatically the boundary pointwise, so they map to homotopy automorphisms of W of the pair boundary of M in W. And then I can forget to self-embeddings of W. And I'm claiming, well, there's still a map like this to absolute homotopy equivalences of W. And I'm claiming that there is a lift like this. This is already slightly non-obvious because on the point set level, this is simply not true. If you have a self-embedding of a compact manifold, it need not preserve the boundary. Think of taking any manifold with non-trivial boundary and pushing, using the self-embedding that pushes the boundary a bit inside. But this is saying that homotopically, I can still recover this action on the boundary. So the way I'm going to prove this is I'm going to rewrite this pair, the inclusion of the boundary in W, in up to homotopy in a way where self-embeddings act in a more obvious way. This is the following lemma. There is which is an elementary lemma that I'm going to pose as an exercise, at least one part of it. I can write the inclusion of the boundary into W up to homotopy as the following map of spaces. I'll take the fibre, and fibre really means homotopy fibre, of the space of self-embeddings of W, disjoint union, an Euclidean space, into W. Then I restrict to only the W in the source to go to self-embeddings of W to W. And this restriction is going to be equivariant with respect to changing the parameterization of the RD coordinate. So I'm going to divide out self-embeddings of RD into RD to the invertible. Okay. And by restricting such an embedding of a disjoint union to the RD part, I get a map to embeddings of RD into W mod reparameterizations of the RD coordinate. And I'm claiming it's a fairly elementary geometric fact that this is an equivalence of pairs. And maybe to give some hint, to solve this exercise, you should use the Collar neighborhood theorem. You should use parameterized isotopy extension. And everything here is topological. And you should use that if you take embeddings of RT into W, well, no. Okay, I think this is enough for hints. No, I'm not going to give more hints because all the other hints are already mentioned in other talks and I want to test whether people listen. Okay, so now what does that buy us? Okay, fine, now we have discovered that we can, to remember the homotopical action on the boundary, we only need to remember the self-embedding and not the fact that it's a homeomorphism. But looking at this formula at this right-hand side, the only thing it involves is spaces of embeddings and naturality with respect to pre-composition, post-composition, all formal properties about space of embeddings. So I can just simply write the same thing by putting T infinity everywhere. And then what's not, well, yeah, it's also an exercise, but using different ingredients, is that the resulting space is still equivalent to this inclusion. So I can literally take the same thing and simply change symbols. I take particle embedding calculus. I replace any embedding space with the corresponding particle embedding calculus space. And to show that there is still such an equivalence, you will need more ingredients, but all of which have been provided by Sanders' talks. To prove the red part, you will use smoothing theory for embedding calculus. You will use naturality of embedding calculus. And you will use convergence of embedding calculus. But given these ingredients, the proof is not difficult and can really be done as without yeah, just knowing these facts. You can replace P essentially by whatever you want, yes. But in some sense, having it for P is the strongest statement because P is the terminal tangential structure. But you could use any other as well, yes. But I mean, in order to even define it, W needs to admit a tangential structure of the sort that you're going to put here. So like you couldn't use framings if W is not frameable, but whatever W admits, you can put there and it will be fine by the same proof. Okay. Well, this does it. Why? Now I've written this pair in such a way that particle embedding calculus self-equivalences of W act. They act by conjugation here, by post-composition here. Everything is equivariant, and tracing through the proof of this, you will see that this is an equivariant equivalence with respect to the action of homeomorph of W on this part. So it provides this. This dotted lift here. That's the proof. So this pair here is acted upon by homeomorphisms of W. That is the this map here. For us, partial zero is empty. Okay, but now I've written it in a way such that the action evidently factors over T infinity of the particle embedding calculus self-equivalences of W, because the action here is induced by conjugation, here by conjugation, and here by post-composition. So that gives me the fact that this action here that records this map factors over the self-equivalences in the setting of particle embedding calculus. That's it. So in general, with this business, what one does is you write down geometric constructions, and then you try to rewrite it only using formal properties of embeddings, and then you can just change symbols and apply these sort of general formal results. So here? Yeah, if you have a lift like that, you in particular give. If I don't put. Yes, but this is stronger. I mean, if I get in particular, I get a lift here and here just by composition. Yes. And I need the strongest version for this big diagram that I drew last time that I'm not going to draw again. Okay. Yes. Yes. Yes, I need that this is a. Pardon, sorry. True. At least not a priori. Yes. So it's a general sort of in the setting where I didn't really want to go into it, but now you asked me about it. In the setting where W doesn't satisfy these assumptions of the theorem, maybe I should write it there, under the assumptions of the theorem, then there is still, the homotopy type on the right-hand side still makes sense. We call it the fake boundary, and you can wonder, even in a more general setting where there is no convergence, what the fake boundary has to do with the real boundary. And we have examples where the fake boundary is different from the real boundary, but not so different. Okay, anyway, but I don't want to go into that. I was about to say you can ask me in the discussion session, but there isn't any today, so you can just approach me. Okay. Say that again, sorry. The white version is completely geometric. That always works. Yes, the red version uses this assumption on tangential two-type equivalence because the proof will involve convergence of embedding calculus. Yes. Okay. Onward. Was there a question? No. Onwards to part 2. Right. So why is this composition null homotopic? And in a sense, everything I'm going to say for the rest of the talk is quite independent of much of what I said previously. So if you're completely lost and you're interested to get back on track. Now is a good time to wake up. Okay, I was asked to sort of, because it has such an omnipresent appearance, to recall again quickly what the ED operand is and what these symbols here mean. So I'm going to do that. So what's the ED operand? It's this operand of little d disk. Disks, one way of describing it is its k operations are embeddings of disjoint unions of open disks. K of them. Here, k lower dash is just a set of k numbers. And I want them to be rectilinear, which means each of the embeddings has to form scalar multiple plus translation for some positive scalar and some Ti in dd. And the operand structure is by composition. Okay. Now, these spaces that appear here, their homotopy type is very simple. I think Sander might have already mentioned this in his talk. If I restrict an embedding of k disks into a disk to the center, I get a map to the ordered configurations. I'm trying to use the same notation as him, to the ordered configurations of k points in a d disk. And this is an equivalence. This one is then also equivalent to just the ordered configurations space of k points in RD. So let's do an example. What is the space of two array operations? This is equivalent to configuration space of 2 points in RD. What is this space? Well, it's homeomorphic to the following. I remember one of the points. And then the only choice I have to use the other point is everywhere but where the first point was. Which is in turn homotopy equivalent to d-1 sphere. So the space of two array operations in this operand is a d-1 sphere. Okay. So what this means is if I restrict to array T2, then an automorphism of ED in the category of operands in particular gives me a homotopy equivalence of the two array operations, which is just a sphere. So this is a homotopy equivalence of an d-1 sphere. This is a space that's typically denoted G of D. Okay, and then I can go further to Z2. Or let me write it like the units in Z, and this map is just given by acting on the top cohomology, or let's say top homology of the sphere. Okay, and I can extend this diagram. There's this action of the group of homeomorphisms on ED that Sander was explaining in his talk, and I can also precompose that with the inclusion by the orthogonal group. Right. Okay, then I can play further games. I can rationalize this operand. Can go to the automorphisms of the rationalized ED operand. That will have the effect of rationalizing all the operation spaces. So by restricting to array T2, I get a homotopy automorphism of the rationalized d-1 sphere. Maybe I call it like that. And by acting on the top homology, which is now a Q, I get a map to Q star. This is the inclusion. Okay. Now I can also precisely say what I mean by these S in front of odd ED. The orientation preserving variants for all of these automorphism spaces are given by the kernel of the compositions all the way to Q star. Okay. That's the first remark I wanted to make. The second one is that all of these automorphism spaces, they come with more structure. They come with stabilization maps that in turn come from multiplication maps. There are external, there are compatible external product maps. And those will be crucial. Okay, let's do it for top D times top D prime. There's a map to top D plus D prime, which just is induced by direct product. If you have a homeomorphism of RD and a homeomorphism of RD plus 1, you can take the product and use that the product of RD and RD plus 1, of RD and RD prime is RD plus D prime. Yes. Okay, similarly, you can do the same thing for all of these automorphism spaces. Let me give you some of the examples that might be less familiar to you. If you take an automorphism of the ED operand and an automorphism of the ED prime operand, then there's an analog of the direct product in the land of operands. It's called the Bodman-Vogt tensor product. This is functorial, and it will give you a map to the Bodman-Vogt tensor product of ED and ED prime, which, by a result that's usually referred to as Dunn additivity, is equivalent to ED plus ED prime. So this is in a point set setting. This was proved by Dunn, and in the fully coherent setting that I'm going to use, this was provided by Jacob Lurie. Okay. There is also a rational analog of this, which comes from a rational version of Dunn additivity. You can also put a Q here. And the version of this version of additivity that we're using for this is was provided by Boavida de Brito and Geoffroy Aurel. Okay, maybe one more example on the level of homotopy automorphisms of a sphere. These external product maps are given by taking joins, using that the join of a D-1 sphere with the join of a D prime minus 1 sphere is a D plus D prime minus 1 sphere. Okay, so there's a lot of structure, and we're going to exploit that structure. Any questions so far? I'm going to say something about that in a bit. So let me postpone the answer to that question. Okay, so how are we going to prove this null homotopy? We are going to first talk a little bit about something called cyclotomic actions. So here's the strategy of the proof of this null homotopy. Let's look at the multiplication map, the external multiplication map for the rational ED-2 operand with the rationalized E2 operand. And that goes to the automorphisms. This preserves the orientations as well, this multiplication map, which follows by the compatibility of the map to Q star. I can take the multiplication, the external multiplication to get to automorphisms of ED, to ED, the rationalization of ED. Now, the automorphisms of E2, potentially non-orientation preserving, acts here by conjugation. And because of the naturality of this external product map, they will also act here by stabilization, by adding the identity on ED-2 on the left and then conjugating. Okay. So what this means is, if I restrict to the automorphisms of the ED-2 operand rationalized, times the identity, if I restrict to that subspace, then this action here will be trivial because the conjugation action on the identity is trivial. So what that means is the restriction of the subspace factors over the homotopy fixed points of this group acting here. Okay. So maybe it's a good time to mention that we're actually going to prove a stronger result than this null homotopy that I was mentioning earlier. This is a result of the two of us. And maybe I should also say philosophically, this is the sort of crucial additional ingredient in extending Weiss's original strategy. This null homotopy is sort of, I suppose, the most novel part of what we do, in the sense that he didn't have this insight that there is this double stabilization map could be null homotopic. Okay, all right. Namely, this is what we show. I already said it in words. This double stabilization map for the rationalized ED operand, also the de-looped version, given by tensoring with the identity on the rationalized E2 operand. This is null homotopic. And we're already provided with a strategy to showing it. We factored it over a different space, so to show that this map here is null homotopic, we could try to show that this guy here is contractible. And this is sort of very much, the strategy to do that is very much in the spirit of old arguments on Sullivan in using rationalizations. The fact is going to be that if we rationalize a space or an operand, typically it has a lot more automorphisms. And these automorphisms on a rationalization on E2, they will act on this space, and they will act highly non-trivial, and they will act non-trivial enough to make the space here contractible. This is what we're going to show. It is really contractible, yes. I should, okay, if I want to be cleaner, I should have de-looped everything here. And then this will be contractible. Yes.
Can you say what how much is known about the homotopy type of these?
So yes, that gives me a way to also mention something else. There is very likely to be a different proof of what I'm going to present by using that there is a formula of the homotopy type of these spaces in terms of graph complexes provided by Frestorch and Willwacher, and subsequent work by Fress and Willwacher. Originally we wanted to use that, and we started doing that. Then we discovered there's an more elementary proof that doesn't use any relation to graph complexes, that doesn't use that there is a formula for these spaces, and this more elementary way is the one that I'm going to present. But yes, there is likely to be an alternative proof of this null homotopy using like the totality of their work on these spaces. Okay, so what are we going to do? I mean, we're going to be very naive in showing that that space, or at least slight variant of that spaces that I'm going to talk about later, are null homotopic. Are contractible. But using that, contractibility is in some sense a much more robust property than null homotopy. I mean, I can check this on homotopy groups, and I can try to compute in a sort of most pedestrian way that I can think of the homotopy groups of that space just by using the homotopy fixed points vector sequence and trying to show that pi 0 of that space acts sufficiently non-trivial on these homotopy groups. So the least I have to know to carry out any strategy like that is some information on the action of pi 0 of this group on the homotopy groups of that. And this is what the next lemma is going to be about. But there is a slight subtle point that I want to not leave unaddressed. Namely, what we're actually going to do is we're going to study the action of that on the automorphisms of the truncated operands. So the space of automorphisms is the limit of the space of automorphisms where I truncate the operand. So I only remember operations of arity less or equal than k. And then I take homotopy fixed points, but this is a limit and this is a limit, so we can equally just study the action
of this group on the truncated versions. And this is what we're going to do. Okay, and the key proposition in that direction is the following. I truncate by arity, yes. So for all degree I and for all dimensions d equal to 2 and for all arity 1, the action by pi 0 of the rationalized E2 operand on the ith homotopy group of the classifying space of the automorphisms of the k-truncated rationalized ED operand is what we call Gr's cyclotomic of non-trivial weight. I'm going to explain that in a minute. And I've been told that this is very close to something that people call the mixed Tate motive, but I don't know what it is, so I'll stick to a name that I can comprehend. Yes. Yes, I'm taking automorphisms in this category of truncated operands, where I only have operations with arity less or equal than k. Yes, it turns out, like if we restrict to reunital operands, that lies. There is a preferred way of extending a truncated operand to a non-truncated operand. So there's a fully faithful inclusion like that. The forgetful functor is a fully faithful right adjoint. Okay, let me tell you what this is. So what does it mean to be Gr's cyclotomic of non-trivial weight? This is a property of an action by pi 0 of the automorphisms of the rationalized ED operand on a group M. And because I'm going to write it a lot, let me introduce an abbreviation. Let me call it GTQ, the group of automorphisms of the ED operand. The reason for this notation is it's actually known, but we're not going to use it, that this group is isomorphic to a rational version of the so-called Grothendieck-Teichmuller group, but we're not going to use that. Okay, so what does it mean to be cyclotomic of non-trivial weight? So M is cyclotomic of non-trivial weight. If there exists a subnormal series, which is equivariant with respect to the action of GTQ, a GTQ invariant subnormal series of this group, how do I want to index it? No, I messed it up, sorry. This is going to be the next definition. It's cyclotomic of non-trivial weight if the group I'm acting on is a Q vector space. And exercise, this is a property, not structure, for a group to be a Q vector space. And the action is given by the following. I take this group, I map it to Q star by acting on the top homology of the arity 2 part. Let's call this rho. This is related to something called a cyclotomic character, but I don't want to go into that. And then I use that, and then followed by multiplication. Sorry, I call it psi, yes. You can call it rho if you like. Let me write it differently, sorry. So I want to act on M by applying the cyclotomic character and then taking it to the power of I times M for some I that is non-zero. Okay, so I could say it's of weight I if it's that I, and I say it's of non-trivial weight if I'm allowed to pick whichever I like. Oh. Okay, then what does it mean to be graded cyclotomic of non-trivial weight? it means that there is a subnormal series, which is GTQ invariant, such that the associated gradient is cyclotomic of non-trivial weight. A finite one, such that how do I do the grading? It's ascending, so I have to do that. Okay. So up to taking the associated gradient, the action is very simple. It factors over the cyclotomic character, followed by some scaling. And it's important that for different quotients, I'm allowed to pick different values of I. It need not, and it must not. No. Yeah, it can be whatever. Yes, as long as it's not not 0. Okay. Right. Let me continue here. Okay, so this is the property we're going to show about this action of these homotopy group on these homotopy groups of the automorphisms of the truncated rationalized operant. And before I do that, I'm going to explain to you why the theorem, this null homotopy, follows from this key proposition. And this will rely on a lemma. I'm not sure exactly who to attribute this. I think the reference I know is in a paper by Drinfeld. And namely, it's known that the answer to the question that was posed earlier is positive. This is surjective. And this is part of what I meant when I said when I rationalize something, it typically has a lot more automorphisms. If I wouldn't consider the rationalized E2 operant, then the only thing I would hit here is plus minus 1, and this would not be enough to make these homotopy fixed points be trivial. But the fact that I rationalized, I have all these scaling automorphisms, and those will make these fixed points trivial. Okay, maybe, sorry, as an exercise, show that being curl cyclotomic of non-trivial weight is preserved by all kinds of operations, namely taking GTQ invariant subgroups, quotients, extensions, etc. So in particular, if one is careful with fringing issues, if some of the groups are non-abelian, this property passes through spectral sequences. All right. So let's prove the null homotopy, assuming the key proposition. Unless there are questions. No? Okay. In fact, I'm going to do a small trick doing that. I won't let the full group GTQ act on it. I just pick one element and I take the cyclic group generated by that one element. This is convenient for something I'm going to do in a bit, probably not necessary, but let me do it. So pick some element lambda that has that lies not in the kernel of the cyclotomic character. This is possible because, in fact, I can realize any unit in Q by an automorphism of the rationalized ED operant. Okay. Pardon? Maybe let's be safe. Sorry? Yes, yes. Thank you. Okay, so because this stabilization map factors over the fixed points of the full group, it in particular factors over the fixed points of the cyclic group generated by lambda. And this is what I'm going to show is null homotopic. Sorry, it's contractible. And I'm going to do that also for finite arity. I already argued that this is good enough. Okay, well, let's get going. What does the homotopy fixed point spectral sequence look like? It's ED, yes. What would I do without you, Marcus? Okay, it's cohomology of the cyclic group acting on the homotopy groups of the space that we're acting on, and then converges to the homotopy groups of the fixed points. Okay, so let me shorten this up a little bit because it's not actually too difficult if you have this key proposition. What is going to happen next? We're going to show that even this whole page with the spectral sequence starts with will vanish. All these cohomology groups are going to vanish. How will we do that? I use the key proposition to show, or not to show, I mean, it immediately implies that it's enough for me to show that the cohomology of lambda acting on any group acted upon by GTQ that is cyclotomic of non-trivial weight is 0. Okay, and how I'm going to do that? Well, I'm going to use the definition. I take the subnormal series, then by sort of taking the spectral sequence associated to this filtration, and I know that I have to be careful that things may not be abelian, and I need to be worried about what H1 means, and so on and so forth, but trust me, it works. One has to be careful, but I'm going to ignore that for here. Up to taking this filtration, it's enough to show it that the cohomology of lambda on anything that is cyclotomic of non-trivial weight vanishes. But then I'm in business. So first I should have written cyclotomic of non-trivial weight, then I argued that in fact it's enough to show that it's cyclotomic of non-trivial weight. But this is a cyclic group, so in particular its generator is central, and I know that it acts by multiplication by chi of lambda to the power of I. So for instance, by something called the center to kill trick, I know that this group is chi of lambda to the power of I minus 1 torsion. But M is a rational vector space, so there is no torsion, so it's trivial. That's it, simple as that. Okay, so everything is reduced to this key proposition, and this is what I'm going to spend the last 10 minutes on. Yes, because do I still have it on the board? No, maybe let me just add it here. If something factors over the fixed point with respect to the whole group, then it in particular factors with respect to the fixed point of any subgroup. For example, the one generated by lambda. Okay. I said that in words earlier. I said that I'm not going to prove that. I think it will be, but this is a trick that makes my life a little bit easier. Okay. No, because you don't know whether you can lift a non-trivial element here to something that's central in all of GTQ. Yeah, but let's not get into that. The thing with lambda works. and it's good enough for what we do. And for optimization problems, there's no time. Yes. Yes. Exactly. Yes. Yes. So I can definitely comment on the history of how this proof came about, which is good that you asked me. I already mentioned Pedro and Geoffroy when I told you about this sort of rational version of the Boltzmann fork tensor product. In the paper where they did that, they gave a new proof of formality that also works in like finite characteristic. And reading this paper was a great source of inspiration for that type of argument. Yes, absolutely. Thanks for that. Okay. All right, so let me tell you a little bit about proof of this key proposition. Okay. But yeah, I won't do this in full detail, but I am going to tell you a little bit about the flavor of it. It is quite computational. I am going to mention all key ideas, but I'm not going to actually carry out the computation. Okay, so we're going to use that there is already sort of prepared method to study automorphisms of operats by filtering by arity, which was introduced by a student of Michael Weiss. So there is a fiber sequence due to Göppel, and then the actual paper. Mike was is an author as well. And what does it say? Well, if we take, can I write it here? Yes. If we take automorphisms of ED, the k-truncated version, let me do it rationally. There is also an integral variant, and I truncate. Then there's a formula for the fiber, which is very close in spirit to the layer identification in embedding calculus that Sander was mentioned. There's a sort of a typical Reedy type situation where you can identify these layers in terms of latching and matching objects. And this is the case here as well. Okay, so how does it look like? Let me give you some space. I take the k-array operations, which is the rationalization of the configuration case space of k points, and the fiber is the space of self-maps of that are firstly sigma k equivariant, and that are under a boundary of a certain compactification of this configuration space that is very much related to the one in Sander's talk, but not actually the same. There's a sigma k action on this boundary, and this map has to be under this space in the derived sense, and it has to be over the limit of taking proper subsets of the set with k points to configuration space on RD labeled, where the points are labeled by S, which also has an action by sigma k by acting on this category I'm taking the limit over. Okay, and there's a rationalization missing here. Yes, thank you. Okay. So I don't want to say too much about what kind of compactification is appearing here. Let me just say that this error here is the rationalization of the boundary inclusion of a compact manifold, and the dimension is given by k minus 1 times d minus 1. Okay. So the space of fillers like that is the fiber over the identity here. All right. Yes? No, I think that version also exists for general manifold. There is something about whether you normalize some distance in this compactification or not. And the dimension, if you, for example, compare with the compactification that Sander introduced, you will realize even the dimension of the manifolds are different. For example, let's do 2 points, then the actual configuration space is something like RD times RD without 0. And then, you can decide, like, for instance, do you forget the RD and compactify just that part and get a D manifold, or do you also compactify this coordinate? So there is some choice on how much you how much you normalize, and this is a different choice here than the one that appears in the layer identification of embedding calculus. But I don't want to make this more precise than that. I see. Yes. Thanks. It is very confusing and very easy to do mistakes with, but I hope we didn't. Okay. Right, where am I at? Maybe continue here. Okay, well, now we need to we're going to induct over arity, use this property that we're going to prove these groups have, namely being graded cyclotomic of non-trivial weight, passes through like exact sequences and spectral sequences like that. So we only have to show that the homotopy groups of this space of fillers has this property. Then I can write this space of fillers as a fibre of the mapping space between the configuration spaces under that to the space of maps from the configuration space to that. So it's enough to show that the homotopy groups of these individual two mapping spaces have this property. And then I can run, like, again, a homotopy limit spectral sequence to compute homotopy groups of mapping spaces. And what I'm going to arrive at the end is the following. Okay, actually, let me just summarize this by saying after several spectral sequences, induction on K, and some tricks. For example, using Poincare duality for this compactification. And always using that this property is very robust with respect to all kinds of operations that are performed in this group. The theorem can be proved, or let's say it eventually reduces to the following. Here is the only fact that we're going to use about the ED operand. I'm going to use that I know the homology of it completely as an operand in graded rational vector spaces. Namely, this is a certain Poisson operand. And the only thing I'm going to use about it is as an operand in Q vector spaces. It is generated in arity 2. And in arity 2, I know exactly how lambda acts by definition. I mean, in arity 2, this is a Q in degree d minus 1, and chi was exactly defined to be the action on this Q. So here, lambda acts by chi of lambda to the power of I. So I'm going to use that. I'm also going to use that I know the rational homotopy Lie algebra of these configuration spaces, and it's as a Lie algebra generated in homotopical degree d minus 1. This is the first non-trivial degree where there is a homotopy group. So this is also just a d minus first homology. And here I already know that it acts by chi lambda to the power of I. So in this deduction modulo of using these spectral sequences, there's one additional non-trivial step. In order to use Poincare duality, you have to figure out how lambda acts on the fundamental class of this manifold pair, and that's sort of a step where one needs some idea to do that. But once one has that, everything reduces to these facts. And this is how one proves this graded cyclotomicity of non-trivial weight. Okay, I'm going to finish here. Thank you. Yes, so where does that appear? Let me do an example. I mean, one thing that in particular appears here will be the mappings, the space of self-maps of that under this, okay? Then if I compute that by like a homotopy limit spectral sequence, what will show up is the relative cohomology here, the relative cohomology here with coefficients in the homotopy here. Then I use Poincare duality of that pair. Then I will get absolute homology of this guy. And this guy is one of the arity spaces in that operant, so I know how it acts there. This is one example of this reduction. Yes. No. I think that one you can. And if you use that automorphisms of the rationalized E2 operant, you know, like because the E2 operant, all of the arity spaces are k-pi1s, so this has a model in groupoids, and then you can explicitly write down automorphisms. I think there's also a way of mapping in. Okay, so in the setting there's a sort of p-adic version of that, and there people I think typically show this, or one way of showing it is that there is a map from the absolute Galois group in that, and then the composition is the classical cyclotomic character, which is known to be surjective. But it's by mapping in subgroups, there's definitely proof of that does not use that the map from that like pi 0 of the automorphisms of the D operant is actually isomorphic to the Grotnik-Teichmüller group. Yeah. Yes. Yes. Exactly. Yeah. So if you take a lambda here, of course, if you use a sort of irrational model of the EET, of the rationalized E2 operant and formality, then you can scale the Browder bracket, and this gives you an automorphism here that lifts that. Yes. Yeah. Absolutely.